Hi everyone. So in this session we look at the equivalent circuit of the induction motor, and by the end of it you should be able to describe the principle of operation, and you should be able to draw and explain the equivalent circuit of the induction machine, including all the steps we take to get to the final equivalent circuit. Now, just as a reminder, this is what the machine looks like, and we have the stator on the outside here in an iron core, and we have the rotor also in an iron core. And the stator, if you remember, is wound in, is a three-phase winding that produces a rotating magnetic field. So what happens now is, as you energize the AC winding, you produce this rotating magnetic field. The speed of rotation is given by 60 multiplied by the electrical frequency over the number of pole pairs. That is the speed of the rotation of the magnetic field in RPM, and if you want it in radians per second, you just multiply by 2 pi on 60 and you could get it in radians per second. Now, why this pole pairs on the denominator here? That has to do with the relationship between the mechanical cycles and the electrical cycles. If you have a cross section of the motor here, and you have N and you have S, and you have one pole pair, which is what this represents, one pole pair and one phase, then as the rotor goes, if you could imagine, I'm going to do it in the reverse way now. If you have north and south, and then the rotor goes, makes one revolution, it will go from north to south to north. So one mechanical revolution in this case will give you north, south, north in one mechanical revolution with one pole pair. Now, if I had two pole pairs, then what is going to happen? I will have north, south, north, south. So in one mechanical revolution, again, I'm going to have north, south, north, south. So I'm going to get north, south, north, south, and then back up to north. North, south, north, south, north. North, south, north, south, north. So I'm going to get two electrical cycles in one mechanical cycle. So when I want to find the amount of mechanical cycles, the mechanical speed of rotation, this is the rotation of the magnetic vector in space. That is dependent on the electrical frequency, but it is also dependent on the number of poles. The more poles you put in the machine, it means more north and south poles there are in one physical revolution that it has to go through. So more poles, it means less mechanical cycles are required to go through that north-south-north combination. So two pole pairs, then I would just need 180 degrees to get through that one electrical cycle, which is north, south, north, right? Or one magnetic cycle, if you want, from north to south to north. So this is why we have the pole pairs on the bottom. This is only because it's AC. Notice in DC we didn't have this problem. The number of pole pairs did not affect the speed because the field is a DC field. So this is only for induction machines, and we'll see for synchronous machines as well. Now, we said we just energize the stator and we end up with a rotating magnetic field, and that rotating magnetic field has a speed which is a function of the electrical frequency and the number of pole pairs. So once the stator field begins to rotate, the rotor is originally fixed, and there's now a relative motion between the rotating stator field and the conductors in the rotor. So an EMF is induced and current flows since the rotor bars are shorted to each other. And since we have now current flowing in the rotor circuit, which is in a magnetic field, we have a current carrying conductor in a magnetic field, it experiences a Lorentz force, and this causes the rotor to turn. Now, the rotor will continue to speed up until the motor, on a continuous basis, which means all the time, provides the torque needed by the load. So when the motor is able to produce the torque required by the load, until that time, it will keep speeding up or slowing down till it gets to that point. And at this point, the machine will stop accelerating and we will have steady state. So of course, to get more torque, you need more force on the conductors, which means you need more current in the rotor, because more current in the rotor, which means a larger current in the magnetic field, so you get a larger force, which requires a larger current in the rotor. Since the rotor is a fixed resistive circuit, requires a larger EMF to be induced in the rotor. And this EMF is a function of the speed deviation. So this is the important part here. The speed deviation is what gives you the voltage in the rotor, which gives you the current, which gives you the torque. So this means that there must always be a deviation in the rotor speed to the stator speed. The rotor is not turning at the synchronous speed. It will always be a little bit less, because you need to maintain that relative motion between the rotor and stator fields, so that you could get an EMF induced, a current induced, and so that you'd have a force exerted on the rotor. If the rotor were to turn at synchronous speed, however, what do you think would happen? So just think about it for a couple minutes. So if the rotor speed was equal to the synchronous speed, then we have the speed difference, the relative motion between them, delta n. This is the relative motion between the rotor and stator fields. Would be 0, and since the relative motion would be 0, then the EMF induced would be 0, and then the rotor current would go to 0. If the rotor current goes to 0, there is no current in the current conductor in the magnetic field, so there will be no force, which means no torque. This means that the rotor will not be able to move the load that it is moving, and the machine will begin to slow down to a lower speed. And we say that the machine would have slipped down from the synchronous speed, because remember, you just need a little deviation to get an EMF induced. So it just slips down from the synchronous speed, and this is what we call the slip. So the slip is the ratio of the difference in speed, the difference in the synchronous speed to the actual mechanical speed, divided by the synchronous speed. So you could calculate it in terms of n in RPM, or omega in terms of radians per second. It doesn't matter. Both of them would give us the same value for omega. Remember, sorry, for S, the slip, remember omega and the speed n are basically the same thing, just in using different units. So if we look at the equivalent circuit now, for the locked rotor, we have some stator windings in a magnetic field experiencing an alternating current, which gives us an alternating magnetic field, which induces an EMF in the secondary. So if you think about it, that is exactly what a transformer does. The only difference between the induction machine and the transformer is you'll have a small gap between the rotor and the stator, right? If you go back, you'll have this gap here, which is simply to allow the rotor to turn. It couldn't turn if there were no gap between the stator and the rotor. So that is the only difference. You have a small break in the core linking the stator and rotor, the primary and the secondary, but once the rotor is at standstill, it is basically a transformer circuit that we're looking at. So you'll see exactly the same transformer layout we have here. We have your leakage parameters with your winding resistance and your leakage inductance. We have the core losses, the magnetization inductance, and then we have the secondary losses and leakage inductance. And we have your turns ratio N1 and N2. So this is exactly the same as the transformer when it is stationary. When it begins to move, however, then we're going to have, let's just go back a little bit. For a transformer, if they're stationary, you're going to have 60 Hertz, let's say we have here. On the secondary, you have the same 60 Hertz because the relative motion of the field with respect to the secondary winding is the same as the field on the primary because the rotor doesn't move. Now, when the rotor begins to move, then that is no longer true. You're going to have a different relative frequency. So this delta N is going to be different. For remember the EMF is proportional to delta N. For the case where it is locked, delta N is equal to Ns because the secondary winding does not move in a transformer. So we have E2 is proportional to Ns. For the case of the moving winding, when the rotor begins to rotate, then it is proportional to Ns, which is the synchronous frequency or the synchronous speed, minus the mechanical speed. So the synchronous speed might be 10 RPM, the mechanical speed, the actual speed at which the motor is turning might be 9.5 RPM. So the difference, the relative motion is 0.5 RPM. So that difference is what gives us the EMF. So if I simply divide these two, I'll see Ns minus S on S. This is equivalent to my slip. So the magnitude of the induced EMF when the rotor is moving is equal to the slip multiplied by the EMF induced when it is not moving. So that is the magnitude of the EMF induced. But what is also affected in this case is the frequency. So whereas in a transformer we have 60 Hertz, and then on the secondary side we will also have 60 Hertz. For the induction machine, once it begins to move, remember the induced EMF here depends on the relative motion. So if I had the rotor turning at say 50 Hertz, then I would just get a 10 Hertz current induced, because that would be the difference, the relative motion between the stator field and the rotor winding. So it is not just the magnitude of the EMF that is induced, that is affected by the relative motion, it is also the frequency of the currents induced and the EMF induced in the rotor, which is affected by the frequency. So again, at standstill, we have delta N is equal to the synchronous frequency because the rotor is not moving. And as the rotor begins to move, just like in the case with the magnitude, it is now proportional to Ns minus N. So we end up with the same relation. The frequency of the rotor current is equal to the slip multiplied by the frequency at standstill. So you see, I say here this F is the frequency of the rotor current at standstill. So you may have in your induction machine, you have a stator current here, 60 Hertz, and if you were, suppose you had a wound rotor machine and you could measure the current coming out, you may get 1 Hertz, which is something strange because you inject a 60 Hertz signal and you get out a 1 Hertz signal, but the remainder of that 15, the difference between these two is actually not in electrical motion, it is in mechanical motion. So it is in the actual rotation, the physical rotation of the rotor. Now, because we have this difference in frequency, then we are going to get some differences in the parameters that we would have calculated for the locked rotor case, for the case where the rotor is stationary. Because remember, you have all these parameters like reactance which are dependent on the frequency. So at the rotor frequency, when the rotor begins to move, the reactance, the leakage parameters, for example, will be 2 pi fl, but now the f will not be the synchronous frequency, but it will be the rotational frequency or the slip frequency, which will be s multiplied by the frequency, the synchronous frequency. So you have two things changing here in your equivalent circuit. You have S on the rotor side being, sorry, let me go back. Right, we have S on the rotor side being scaled by, the E2 on the rotor side being scaled by S to give us the magnitude of the impedance if the rotor is moving, and we have the inductance also being scaled by S. Of course, the resistance is not dependent on the frequency. So what we're going to do now is we're just going to look at the current in the rotor, IR, this current here, which is simply the voltage SE2 divided by the total impedance R2 plus JSX2. So I could divide by S on S, and I could bring it to this form, IR. So the same IR is equal to E2 divided by R2 on S plus JX2. So I could convert the rotor at any speed, from this circuit to this circuit. Now this might seem like a very simple thing. All I did was divide by S on S. S on S is 1. So I divided by S on S. How different could the circuits be? Now, the current in the circuit is the same. But, and this is a very important point to note. So if you have zoned out, pay attention now. These two circuits are fundamentally different. Even though the magnitude of the currents are the same, here the real power dissipation is I squared R, IR squared R2, and this one, it is IR squared by R2 on S. Remember, I don't know why that keeps happening. Anyway, remember S is a fraction. So R2 on S is going to be more than R2. So how did we end up with more power in this circuit than in this circuit? What does that extra power represent? So what it represents is, in this case, we have the actual rotor circuit. This represents the electrical parameters of the rotor circuit only. So we have the R2 multiplied I squared R2 here. This represents the copper losses. The frequency of the current and voltage here is the frequency of current and voltage that you would measure if you could measure those currents in the rotor circuit. If you could take your oscilloscope and measure it, the frequency of the current here would be that frequency. In this case, we have the frequency is equal to the synchronous frequency, because we didn't go through that division, that scaling by S. This frequency is equal to the synchronous frequency. This added resistance represents the mechanical load. So this circuit now captures both the losses, the electrical losses in the rotor, and the useful power which is converted to mechanical energy. So the mechanical, this R2 on S, represents both the electrical losses and the mechanical power, and that is why it is fundamentally different from this circuit, even though you just divided by 1. S on S, we actually changed what the resistances were in the circuit. So it is not a simple concept, it is not a simple transformation at all. You have to understand what went on here very well if you want to understand the development of this equivalent circuit. Now, the next thing we're going to do that we have this is we're going to just refer the parameters from one side to the next, and we do this exactly the same way we do it in a transformer. Now, for an induction machine, we don't actually know what the turns ratio is, but if you try to measure the parameters, what you would be measuring are, in effect, what you'd be measuring is the values referred to one side. So we don't ever see what, in a squirrel cage motor say, we don't actually ever measure what the actual parameters are in the rotor. We always would measure them referred to the stator. So we refer everything, which means you simply multiply by n1 squared on n2 squared to go to the primary side. And what we end up with is, instead of x2, x2 prime, and instead of r2, r2 prime. So the next thing we're going to do, that we've brought everything to one side like this, is we're going to split the rotor resistance, that R2 on S, into R2 prime, which represents the rotor copper losses, and if we just say R2 on S minus R2, that would give us R2 on S multiplied by 1 minus S. This is simply R2 on S minus R2. So all I did there was I had R2 on S here. I had R2 on S, here, and I just wanted to take out the R2. So I subtracted R2 and put it here, and the remainder is this. So this now I could see clearly the stator copper loss, the magnetization loss, the rotor copper loss, and this resistance here represents the mechanical load, the power that will go to the actual load being turned. So this is the, well, not the final equivalent circuit. There's one more simplification we could make. And if you remember your transformer circuit, what we're going to do is simply move the core branch from one side to the next, which is a good assumption if you remember, because the core parameters are very much larger than the leakage parameters. So once we move that, we could add up the rotor and stator losses and the equivalent and the leakage inductances and so on, and we could come up with one value for them, which is what you'll be finding in your labs and so on. So this is the equivalent circuit that we're going to work with. So you'll see you have, almost just like a transformer, you have magnetization loss or no load loss. We have the magnetization inductance, leakage inductance, equivalent circuit. All of this is at 60 Hertz or whatever is the electrical frequency, because the electrical frequency, even on the rotor side, part of the frequency goes to the mechanical rotation, part goes to the electrical current in the rotor. So this circuit captures both of them together. So I hope by now you should be able to describe the principle of operation of the induction machine. If it's still a little bit confusing, go back through the video, note down the points where they're a little bit muddy, and we will go over it in class, but really try to figure out what are the specifics that you need to know so we could go into it in more detail and draw. And you should also by now be able to draw and explain the equivalent circuit for the induction machine. Next time we will begin looking at power and torque, and then we will start doing some questions.